Okay, so let's do another shear flow calculation for a thin-walled member. First off, let's go ahead and figure out our calculations for the eye. A bit more complex than the last one, but so I'm going to break this up into three distinct sections. So I got the red thing on the top, got the green on the bottom, and let's go for purple on the sides. So each of those, we're going to have an A, a Ybar, and an I calculation. Actually, let's space that out a bit more. So for the top one, the area, 0.5 inches, here, what's its length? So 2 inches plus 0.5 plus 6 plus 0.5 plus 2. 11 inches total. Length, that there to there is 11 inches. So our area, 11 times 0.5, 5.5 inches squared. I'm going to keep measuring from the base up for our initial Ybar calculations. So let's see here. Based upon that, we've got 6 inches plus half of 0.5 inches, so 6.25 inches. I'll put that in. Yeah, put that like that. And then our I calculation, that'll be 0.5 inches to the third times 11 inches divided by 12. So that'll be 0.115 inches to the third. You know what? I'm probably not going to need that many decimal places because it's going to be completely overwhelmed by the other ones. But anyways, for the green, let's see here. So its width is 7 inches, and its thickness is 0.5 inches, so 3.5 inches squared. Its Y-bar is half of 0.5 inches, so 0.25 inches. And its I, 0.5 to the power of 3 times 7 divided by 12, 0.073 inches to the third. And then the purple. So this is per each one, so later on we'll multiply by 2. But let's see, its height is 6 inches minus the 0.5 inches, so 5.5 inches times its thickness of 0.5 inches. So total area 2.75 inches squared. Its Y-bar location, 5.5 inches divided by 2 plus the 0.5 inches from the base there. That'll give us 3.25 inches. And then its I calculation is 5.5 inches to the third times 0.5 inches divided by 12. So, like I said, probably didn't need to the 3 decimal places for the previous ones. 6.93 inches to, wait, inches to the fourth. What am I doing here? That's inches to the fourth for each of those, not inches to the third. My bad. Sorry about that. Okay, so calculating the location of the centroid for this cross section. So I guess we'll define our coordinate system first. So this is z-axis. And we'll put y-axis up here. So our y-bar will be equal to, again, the sum of the a prime times the y bar prime divided by the sum of the areas for each of those. So let's see here. We've got 5.5 inches squared times 6.25 inches plus 3.5 inches squared times 0.25 inches plus 2 of these times 2.75 inches times 3.25 inches. All of this over the sum total of the areas, 5.5 plus 3.5 plus 2 times 2.75 inches squared times 6.25 plus 3.5 times 0.25 plus 2 times 2.75 times 3.25, all divided by 5.5 plus 3.5 plus 2 times 2.75. So that gives us a y-bar location relative to the base of 3.66 inches. So now to figure out what our I calculation is, again, that is just the individual components added together plus the we're invoking our parallel axis theorem, so plus the area times their y-bar squared. Again, that's the y-bar relative to the centroid. So starting on the top, got the 0.115 inches to the fourth plus 5.5 inches squared times 6.25 inches minus 3.66 inches squared plus 0.073 inches to the fourth plus 3.5 inches squared times 0.25 inches minus 3.66 inches squared. And then the purple plus 2 to them times 6.93 inches to the fourth plus, again, 2 times 2.75 inches squared times 3.25 inches minus 3.66 inches, all that squared. So, okay, so adding all that together ends up being 92.56 inches to the fourth. So we want to be looking at shear flow at points A and B. So I'm going to actually just zoom in a section here. So if you look at it, they're actually looking at A just to the left of where that weld is. So we're really trying to look here. So basically just the shear flow that's developed in this segment here. So not at the joint there, kind of a bit to the left there. So go ahead and calculate that. So if we're just looking at, looking at it across there, and we're basing our Q on this cross section here. So again, so that's the 2 inches that are sticking out to the side there. So our Q, so this is 2 inches and this is 0.5 inches. Our Q is going to be, I'll do that over here. Q is equal to A times Y bar. So that'll be 2 inches times 0.5 inches. And then the Y bar there is the overall Y bar of 3.66 minus the Y bar of that location of 6.25 inches. So let's see. Like I said, technically speaking, we're looking at 6.25 minus 3.66. But that really just changes the directionality, which we're not really all that concerned about. We're looking at the magnitude. So 2.59 inches times 2 inches times 0.5. That gives us 2.59 inches to the third. So finding our Q at A is going to be the load, the V was 7 kips. So 7,000 pounds force times 2.59 inches to the third, all divided by the I, which is 92.57 inches to the fourth. Sorry, 5/6. So inches to the third on the top, inches to the fourth on the bottom, as well as the pounds on the top. That ends up giving us 195.9 pounds per inch. So yeah, next up we're going to look at Q. So Q here, yeah, that is on the joint there. So I guess, actually, now that I think about it, it's kind of irrelevant at that point because it doesn't have the, down below, we don't have the kind of the two, we don't have anywhere for that flow to split. But again, we just need to figure out what our QB there is. So here, we're just going to go ahead and take, well, here, let me sketch this. Let me sketch what's going on here. So essentially, we're going to have shear flow going this way and shear flow going this way. So the easiest, it's symmetrical. So the easiest way to do it would be calculate the shear flow based upon this entire Q and then just divide by 2. So for that segment there, our area is the 0.5 inch thickness times its width of 7 inches. And then times its Ybar of the 3.66 minus the 0.25 inches. So from the centroid down to the thickness of that segment there. And what does that give us? That's a QB equal to 11.94 inches to the third. So for shear flow at B, that's going to be equal to the 7,000 pounds times 11.94 inches to the third, all divided by 92.56 inches to the fourth. 7,000 times. Oh, and divided by 2. Because can't forget that. So that'll give us 451.5 pounds per inch. As for the Qmax, that is going to be occurring at the neutral axis. So essentially what we need to do is, we've got this, we need to figure out what the Q would be. So if here's our neutral axis, we need to figure out what the Q would be for this, this shape here. So we know that this is 3.66 inches, and this here is 0.25 inches, and this, oh wait, no, 0.5 inches, not 0.25 inches. And this here is also 0.5 inches. And this here is 7 inches, which makes this here 6 inches. So the let's see, the area for that cross section segment is fairly simple to calculate. So I'm gonna, the area there is 7 inches times 3.66 inches minus 6 inches times 3.66 minus 0.5 inches. So essentially the entire box minus the size of the box in the middle. So that gives us a 6.66 inches squared area. So yeah, that is its area. Now we need to figure out what its centroid is relative to the centroid overall. So I guess we could just do the, use the similar calculation, similarly defined areas, the big box and then the neutral space. So to figure out what our Ybar is, let's kind of define this relative to this neutral axis here. So our Ybar there relative to the neutral axis that is going to be the 7 inches times 3.66 inches times, we'll measure positive as being down from there. Simple, rather than have to worry about negative signs for that. Times 3.66 divided by 2. So that's the area times the y-bar. And then since this space here is negative, we subtract. So 6 inches times 3.66 minus 0.5 inches. And then times its y-bar location, which is just this again divided by 2. You know what? I'm actually just going to put, rather than writing that out again, I'm just going to put a squared sign here and divide by 2. You know what? I'll do that over here too. So that's the top of our formula, and then bottom here, 7 inches times 3.66 inches minus 6 inches times 3.66 minus 0.5. So what do we got here? 7 times 3.66 squared divided by 2 plus 6 times 3.66 minus 0.5 squared divided by 2. So value on the top is 76.84 inches to the third. And the value on the bottom, 7 times 3.66 minus 6 times 3.66 minus 0.5. Oh, I had already calculated that. 6.66. Duh. Inches squared. So that gives us a y-bar calculation for that area of... That doesn't seem right. No, that can't be right. Oh, yeah. That was incorrect because I've screwed up the calculation over here somewhere. That should be 16.9 inches to the third. Divide by 6.66. There we go. That is a far more reasonable 2.54 inches. So that's the centroid of just that section there. So our Qmax is equal to QV over I, 2.54 inches times 6.66 inches squared times 7,000 pounds force, all divided by, what was our I again? 92.56. 6 inches to the fourth. Oh, and divide by 2 again. Because, Again, that'd be like the maximum shear flow. Split up over these two sections. So that'll give us 639.6 pounds. Actually, here, let's make that 640. Is our shear max, our shear flow max. Yeah. And there we go.